My understanding of it, let me know if this is right, is that the centripetal force is a resultant force. You take whatever forces are acting on an object, and if that ends up causing the object to travel in a circle, you call it a centripetal force.
I think that's right. And it's
I
not
guess
a force in the sense of like tension or a push force.
Perfect.
It's what the forces sum up to be to make circular motion.
Mm-hmm. And I guess that's like central walk force. So it's like if you have an object and it has to go, it moves in a circle, the centripetal force is what's pulling it in there. And I like your example of tension. So say we have like a pole and a tether ball that's going around. Like there's no, like what is a centripetal force? There's no, like, well, there's no object pulling, there's no A on B object pairing. What there is though, there is the ball on the pole that's being pulled by the tension. And so the portion of the tension that is pulling in towards the middle, that portion of the tension is the result is what we call the centripetal force.
Mm-hmm.
Okay.
Like
We've defined centripetal force. We've defined gravity. And so let's see how that plays into here. So there's this graphic, very nice graphic, but I'm not sure I get it. So here's the moon, here's the earth, here's the bulges, and they drew these blue forces. So this blue force is the centripetal force.
Okay.
And they said that it's constant everywhere. And so constant everywhere pointing to the left, I guess.
There's no way that centripetal force can make any sense to me. Because if we're talking about the centripetal force for Earth's rotation, then the centripetal force should always be pointing towards the center of the Earth. Right?
So I guess I would say yes on the horizontal, like on the equator. But I think when you're up in the North Pole, the centripetal force always goes towards the center of rotation. So right now, the center of rotation is in the middle of my cup, which means the centripetal force is always just inward, in towards the middle.
Yeah. So in a cylindrically symmetric fashion. So,
yes. Thank you.
So
thank you. Yeah.
If you're looking at the Earth from the pole, then it's always in towards the center. But if you come off, then it has to be in towards this line that is up through that shoots from the South Pole to the North Pole.
Yes. Thank you. Yeah.
Yes. But
like not
the
to
important
the core.
part
Okay. To the axis.
And it's not going to be the same at each point on the Earth. Like if you're at the pole, there's no centripetal force because it's not in any circular motion. And at the equator, it's going to be maximum.
Right.
And it's going to go from the equator at maximum to 0 at the poles.
Right.
So it's not the same everywhere on the Earth.
Exactly. But here it's drawn the same everywhere.
Yeah. If it's the centripetal force due to the Earth's orbit around the center of Earth Moon center of mass, meaning because the moon and the orbit do.
Right. So the center of mass is somewhere here. Yeah.
So the centripetal force in that case has to point towards the barycenter, which is somewhere in the middle of the Earth, somewhere in the Earth, off center.
The axis. Yep.
Still, which means on one side of the Earth it's going to be pointing one way, and on the other side of the Earth it's going to be pointing the other way.
Agreed. Let's make it concrete. So here's the barycenter for the sake of argument, not in the middle, a little bit off to the side because of the moon. So then that means that the Earth and the moon are rotating around this axis.
Yep. Which
means the centripetal force, which by definition must be towards the center, the axis of rotation. That means on the right side, from this side of the Earth, the centripetal force should be pointing towards the axis.
Yep.
And on the left side of the Earth, the centripetal force should also be pointing towards the axis. That's in towards the center, in towards the barycenter. This is definitely wrong.
It's definitely wrong, right? So this, because you talked to me about this, and I started looking some stuff up in some textbooks.
Excellent, yeah.
And I can't find an explanation for this. It seems to be just stated as fact. Right. And I don't know what frame they're in. I don't know what's going on. I don't know where this came from. This is a bunch of crap.
Yeah.
Like,
I couldn't figure it out. But I have an explanation that felt good. Professor said to me, seems right. But then years later, I looked it up, and I cannot figure out what's going on here.
Right. Gosh, and as a physics student, it's like tides are important, but it's not so important
Okay.
It's like you kind of just go through the motions.
Yeah.
And now years later, we're looking at this and we're like, What
happened?
What happened? I don't understand it.
Is the professor like at a dinner party like like what I told these kids?
Is this one of those things where everyone is like, somebody figured it out some time ago? It's fine.
It seems
like,
fine.
I don't
Whatever.
get it. Whatever. It's not important for my career. Whatever.
And there's some
like
tideologist watching our channel is like, yes, finally someone said it.
something. Yeah. And we're like, and nobody, there's just so many misconceptions all over the place. And everybody's like, yeah, tides, whatever. Newton's laws. We got it. No problem.
But this explanation
nobody
seems
understands
fine. We have two tides. Seems to be okay, but actually wrong explanation.
Okay. Either this explanation is like wildly wrong, or there's some like problem solving trick that we don't understand. It's like move to the frame where the centripetal force is the same everywhere. I don't know why you would do that. That's like a wild transformation. But then if you do that, it's super easy, and then you just translate back later.
Yeah, and it's like some super smart person figured it out in the whatever hundreds, and then everyone and they're like, proof looks good, and somebody's like, seems fine. Like, okay.
And from then on, everybody was like, seems fine.
Seems fine. Like, I can't monetize this. Like, seems fine, dude. Like, your theory is great.
That's right. Is this helping us in any way? Not really. Then it's fine.
Whatever, let it go. I got other stuff to do.
Although now I'm upset because I don't understand it, and I've been doing some rabbit hole stuff. I still can't find it. So I'm going to be going into the 18th century, 19th century, some like treatises. A treatise on tides by Joseph, McSorley from England.
Like, what did your family do? We're tidesmen. We figured it out. But this, it makes sense. Like, it looks good. So if you have the centripetal force going in, and then the gravitational force going out, the net result is a gravitational force that pulls out. This seems great. Same thing down here. Centripetal force is going in. The gravitational force is coming up and to the right because it's towards the moon. And the net result is no. Gravitational force is this one, the red one, going up and right towards the moon. And the net result is this force here in the middle that gives you a bulge. Seems great. And then on the far side also seems fine. If you have this centripetal force, which is going to the left, gravitational force going to the right, then if these magnitudes work out like that, you get a little bulge here. But this can't be going to the left. Centripetal force has to go in towards the axis of rotation.
Right.
Which means you should have like a cavity here.
Yeah. Why? Well, that means why would as you said, the centripetal force just work out like that? Like, it has to be this exact magnitude to give us the two bulges. If the centripetal force is not the correct magnitude, then it could just be one bulge.
Right.
So why is the centripetal force like dialed into this particular magnitude? That doesn't make sense.
Why? Why did it work out like that? And more hate on this. It's why did on the right side we invoked gravity? Like a clear, easy Earth pulling on the water pulling on the Earth. Moon pulling on the water, pulling on the moon, like a clear physics, like a clear, well-known interaction, like one of the four fundamental forces. And on the far side, we were like, I can't do that. I'm not going to do a Newton's third law argument. I'm going to do this workaround thing. Like, no, give me the direct rule. Give me the direct physics. Why are you doing this sidesteppy stuff?
That's right, because it's all the Earth. Why are we suddenly changing, I don't know, analysis techniques after we
don't like it.
Cross, like what the heck?
It's like, it's cherry picky. That's the thing that I don't like. It's like for all these things I have these rules, and then here's this physics, I'm going to explain it. But this one I'm going to not do those. I'm going to use this one thing that works. I'm like, there we go, cherry pick, it works.
Yeah, and I have no way of taking this explanation and being like, let me analyze other planet moon systems. Does it have one bulge, two bulges? Like, where is the bulge? Like, in complete loss.
Okay, well, I don't know. I don't know what the answer is.
I don't know. We will get back to you guys because I don't understand tides.
I don't understand tides.
I don't get it at all.
Like, twice a day, sure. That's what I see. Like, sure. I know it's true, but why?
Yeah. I'll be reading some textbooks about bulges coming up. Bulge physics.
Yep. There's always one in the front and one in the back. And I think the one in the front is bigger. That's just a fun
Are they
fact.
the same size? The front and back bulge, are they the same size? Or
I
is
don't
it?
think so. I think you get a high tide and a low high tide. I think there's also a super tide. It's like if you have the sun, I guess it would be like way out there. But if you have the gravitational force from the sun and the gravitational force from the moon all like in the same direction, you get a super high tide.
Right. So that's like, the moon and the sun both create tides
all
independently.
aligned.
And if they're aligned, you get a super bulge. And if they're not aligned, you get a,
Super low.
super low bulge.
I guess maybe that happens if you get a super high tide on the other side of the Earth. Are you getting that super low tide simultaneously? I think so.
I think if you get a big bulge in front, you get a big bulge in back.
Think so?
I think so. I mean, okay. Yeah, with the intuition that I've gained from this crazy, awesome picture.
Yeah,
I think so.
I hate it.
I don't know. So is it like a super tide would be like ultra big bulge in front and almost no bulge in back?
Exactly.
Or do they get both get big? I don't know.
I don't know. I'm not a tidematologist. Oh well,
Well,
we
get back to you
will
guys.
do some research
Yep. See you guys next time.
next time on us, our channel.
Our channel. That's right.